Mounting is one of those Linux topics that feels simple when you first learn it, because it sounds like you are just attaching storage so you can use it. But the exam leans into mounting because it is where many real failures show up after changes and reboots. The tricky part is not the idea of mounting itself, but the fact that mounting involves persistence, timing, and identity, which means the system must be able to find the right storage at the right moment and attach it to the right place every time. When that does not happen, people experience boot time surprises that feel dramatic, like missing data, missing services, or a system dropping into an emergency environment. This episode is about turning mounting into a calm mental discipline, where you can distinguish between mounts that exist only for a moment and mounts that must persist across reboot, and where you understand why the mount configuration file is so central to system reliability. By the end, you should be able to explain the role of fstab, describe what transient mounts are and when they make sense, and identify the common mistakes that cause boot time mount failures. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. The first concept to lock in is that mounting is the bridge between a file system that exists on storage and a live directory tree that programs actually use. A file system can be perfectly healthy and still be invisible to the running system if it is not mounted, because Linux does not automatically attach every discovered file system to the tree. Instead, mounting is an intentional act that says this file system should appear at this mount point, and from now on, paths under that mount point are interpreted using that file system. This matters for exam reasoning because many scenarios that sound like data loss are actually mount problems, where the data still exists on disk, but the file system is not attached to the directory where the user expects it. It also matters because mount points are just directories, and a directory can exist even if nothing is mounted there, which can trick beginners into thinking everything is fine because the path exists. The reality is that the path is only meaningful if the intended file system is mounted on it, and otherwise the path refers to the underlying directory on whatever file system is currently mounted above it. The exam tests this by describing situations where files appear to vanish or where a service cannot find its data, and the correct explanation is often that the expected file system is not mounted. When you learn to treat mounting as the visibility layer, you stop jumping to the conclusion that disks are empty or corrupted. The next concept is persistence, because not every mount is meant to last forever, and understanding the difference is essential for avoiding surprises. A transient mount is a mount that exists for the current session or for a specific purpose, like temporarily attaching a removable drive, accessing an external backup, or mounting a file system briefly to inspect or copy files. These mounts are intentionally temporary, and the system does not need to recreate them automatically after reboot. A persistent mount, by contrast, is a mount the system must recreate at startup so the environment is consistent, such as mounting a separate file system that holds application data, user home directories, or important logs. The exam wants you to be comfortable with both ideas, because different scenarios call for different approaches. If a question describes a one-time task, a transient mount is often the safer and simpler choice because it avoids modifying boot configuration. If a question describes a system requirement that must exist every time the machine starts, a persistent mount is required, and that is where mounting configuration becomes critical. The student's skill is to match the mount type to the intent and avoid turning temporary needs into permanent risk. Persistent mounts are typically described and managed through a configuration file that tells the system what to mount during boot, where to mount it, and under what rules. On the first mention only, that file is File Systems Table, fstab, and its role is to act as a declarative map of the mounts the system should establish automatically. The important exam-level idea is that fstab is not just an optional convenience file. It is a core part of boot time storage reliability because it defines which file systems must be present and how they should be identified. If the entries are correct, boot time mounting is predictable. If the entries are wrong, the system may fail to mount critical file systems, and depending on what is missing, the system might still boot, but behave strangely or might fail to reach a usable state. Beginners sometimes think of fstab as a place where you list drives, but a better view is that it is a contract between the system and storage. At boot, the system expects these resources, and it will act based on whether it can satisfy those expectations. The exam uses this because it tests whether you understand that persistence is a configuration decision, not something the system guesses automatically. When you recognize fstab as a boot contract, you will interpret questions about boot surprises more accurately. Identity is the next pillar of mounting mastery, because the most common cause of boot time surprises is the system mounting the wrong thing or failing to find the right thing due to fragile identifiers. Device names that depend on discovery order can change between boots, and the risk increases as systems add more disks, removable devices, or complex storage layers. This is why stable identifiers matter, because stable identifiers keep the boot contract consistent even when the environment changes slightly. Earlier, we introduced universally unique identifier, UUID, as a stable identity concept. And here the key idea is that fstab entries often rely on stable identifiers so the system can find the intended file system reliably. If you use a stable identity, you reduce the chance of mounting a different disk just because it appeared first at boot. The exam often hints at this with scenarios where a system was fine until new hardware was added or a device order changed, and then mounts started failing or pointing to unexpected places. The correct reasoning is that the mount configuration relied on an unstable identity and the environment changed, not that the file system randomly vanished. Identity thinking is what turns a confusing story into a predictable root cause. Timing is another frequent source of boot time surprises, and it becomes obvious once you remember that boot is a stage process where not all devices and services are available immediately. Some devices, especially certain storage types or network-based storage, may not be ready at the exact moment the system tries to mount them. A file system might exist and be healthy, but if the device is not ready, the mount attempt fails, and the consequences depend on how critical that file system is to boot. If the root file system itself cannot be mounted, the system cannot proceed normally. But if a non-critical file system fails to mount, the system might still boot while leaving that mount point empty. The exam often uses this by describing a system that boots into an emergency environment because a required mount failed, or a system that boots, but then an application fails because its data mount was not present. In both cases, timing and readiness can be part of the explanation, especially if the storage depends on network availability or on a device that takes time to appear. Mounting mastery includes recognizing that boot time mounting is not the same as mounting later in a fully running system. The student-level takeaway is that a mount can fail not because it is wrong in principle, but because it happened at the wrong time or with unmet dependencies. Another practical part of mounting mastery is understanding how mount points behave, because the mount point directory is not destroyed or changed when you mount something on it, and that can hide content and create confusion. If a directory already contains files and you mount a file system on top of it, the original files become hidden behind the mounted file system. When the file system is later unmounted, the original files reappear. This can produce a scenario where someone thinks data vanished because they mounted a different file system, wrote files, and then later unmounted or failed to mount on reboot, revealing a different set of files than expected. The exam can use this to test whether you understand that mounting changes what a path refers to, and that a path can refer to different underlying storage depending on mount state. A beginner misunderstanding is thinking the path always points to the same physical storage, but in Linux the path is an abstract location in the tree that can be backed by different file systems. Mount points are therefore not just locations. They are attachment sockets that change what lives below them. When you treat mount points as sockets, you stop being surprised by the hide and reveal behavior. Transient mounts fit into this picture as a safety tool, because they allow you to attach storage for a task without altering the boot contract. If you have a removable drive or a temporary data transfer need, a transient mount is often the right approach because it limits the scope of change. The exam sometimes frames this as choosing the best approach for a one-off operation, and the safest answer often avoids making persistent configuration changes for temporary needs. Transient mounts are also useful when you are troubleshooting, because you can mount a file system temporarily to inspect its contents or to confirm it is healthy, and then unmount it without affecting future boots. This aligns with the exam's preference for minimal risk actions that match the goal. Persistent mounts are powerful, but they create responsibility because you are now depending on that mount being correct at every boot. Transient mounts keep you flexible when the need is temporary, and they reduce the chance of future surprises because they do not change system startup behavior. Understanding this distinction helps you choose appropriate answers in questions that ask what you should do, not just what you could do. Avoiding boot time surprises also involves knowing which mounts are critical and which are optional, because the consequences of mount failure depend on what the system is missing. If a mount holds essential system components or required application data, its absence can prevent the system from reaching a functional state or can break important services. If a mount holds optional data, its absence may be annoying but not catastrophic, and the system can still boot and allow you to troubleshoot. The exam may present a system that drops into an emergency environment and expects you to realize that a critical mount failed, while another scenario might describe missing data in a non-critical location and expect you to realize the system booted, but an additional file system was not mounted. This is why mounting mastery is not only about attaching storage. It is about designing predictable startup behavior and understanding what the system depends on. A good mental habit is to imagine what happens if that file system is missing at boot, because that reveals whether you should treat the mount as a hard requirement or a best effort resource. Even without configuration details, this habit helps you interpret the severity of symptoms. Verification is the bridge between theory and safety, and it is one of the most consistent exam skills you can apply to mounting. Verification means confirming that the system is actually mounting what you think it is mounting at the mount points you expect, using the identifiers you intended. It also means verifying behavior across reboot, because many mounting problems do not show up until the system restarts and device ordering or readiness changes. Beginners often verify only once, in the moment, and then assume the change is permanent and reliable, but the exam often tests scenarios where a change seemed fine until reboot. A strong learner trains themselves to think, what will happen the next time the system starts? And does my mount identity and timing model still hold? This is where stable identifiers pay off because they reduce surprises, and it is where understanding dependencies pays off because you can anticipate which mounts might fail early. The exam rewards this mindset because it is evidence-driven, cautious, and realistic. Mounting mastery is largely about not trusting assumptions and instead confirming that the system's live state matches your intended design. Common failure patterns also include confusing mount failures with file system failures, and the exam can exploit that confusion by offering answers that operate at the wrong layer. A file system can be perfectly healthy but not mounted, which is a mount layer issue. A mount can fail because the file system is corrupted or incompatible, which is a file system layer issue. A mount can fail because the device cannot be found, which is a block device or identification issue. A mount can fail because the partition map changed, which is a partition layer issue. Your job is to use the story clues to identify which handoff in the chain is broken and then choose an answer that targets that handoff. If the story mentions the device is missing, a file system check answer is likely wrong because there is nothing to check. If the story mentions the file system exists and is readable when mounted manually later, then a corruption explanation is less likely than a boot time timing or configuration explanation. These distinctions are what make mounting questions manageable under time pressure. When you keep the storage chain fully intact, mounting mastery becomes a method, not a set of isolated facts. By the end of this episode, you should be able to explain mounting as the attachment layer that makes file systems visible within the Linux directory tree, and you should be able to distinguish between transient mounts for temporary tasks and persistent mounts that must be recreated at boot. You should understand fstab as the boot contract that describes persistent mounts, and you should be able to explain why stable identifiers like UUID values reduce boot time surprises by preventing device order changes from breaking the contract. You should also be comfortable with the idea that mount failures can be caused by identity, timing, device readiness, or file system integrity, and that the right interpretation depends on where the failure occurred in the storage chain. Most importantly, you now have a practical way to avoid and to diagnose boot time surprises. Treat mounts as deliberate contracts, Choose persistence only when needed. Use stable identities and verify behavior across reboot rather than trusting a single successful moment. That mindset will carry directly into the next lesson on mount options, because once you can mount reliably, the next question becomes how to mount safely and stably with the right behavior choices.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.